Okay, so let's start from where we left off. So the next one is using the sandwich theorem. And let's see what this one says. Here we have a function f that is trapped, or that is the values of f are trapped or sandwiched between these two other functions for this range of x, that is x lying between -1 and 1. We have to find the limit of f of x as x approaches 0. Okay, so to be able to use the sandwich theorem, we have to know what the limits of these two functions are as x approaches 0. So let's see that first. Solution. We have, using the various limit laws, that is power rule, product rule, such things, we get these limits. Equal to square root of 5, and you can clearly see that the limit of this will also be the square root of 5. So by the sandwich theorem, this limit should also have this value. So by the sandwich theorem, we have this. So the power of this theorem is that regardless of what the function f actually is, the limit should have this value only, and the limit exists. Okay. Now the next exercise, and in fact the next 3 exercises are exactly similar. So I am going to leave exercises 44, 45 and 46 to you. Okay. Now next, let's see theory and examples. Under this heading, we have exercise 47. If, again here also we have some function f whose values satisfy these inequalities. For x in this closed interval between -1 and 1, and at the same time we also have these inequalities for x less than -1 and x greater than 1. The reason for having two separate sets of inequalities is because depending on where x is lying, either x to the power 4 is less than or equal to x squared or greater than x squared. Okay, so that's why we have two things. Okay, so if these are the things, if these are our hypotheses, at what points C, do you automatically know the limit of the function f, which of course would come from sandwich theorem again. Automatically know the value of this limit. What can you say about the value of this limit at those points? So we have to apply the sandwich theorem here, right? Because we don't know what f is. So in this situation, in order to answer this question, the only way to have this is sandwich theorem. Now for sandwich theorem, you then would have to know the limits of these functions, the fourth power of x and the square of x, at some point c, okay, and such that those two limits are equal, because then only we are able to use the sandwich theorem. So let us start the solution like this. Let C be a point. Point means a real number such that limit of this is equal to limit of x square as x approaches c. Then, but the limit of this is the fourth power of c and the limit of this is c squared. So from this equation we get three values of c: -1, 0 and +1. You can solve this equation and get those three values easily. And so -1 or 0 or 1. Thus, by the sandwich theorem, limit of our function f, okay, we have to write the three cases separately, right? So let us first take -1. It will be what? It will be, you can either calculate the square or the fourth power, it does not matter, because we have found these values in such a way that this equation is true. So let's consider square. So this is going to be 1. That is one thing, one limit. If x is approaching 1, then also this limit is 1, because here we have square of minus 1, here we have square of plus 1, and when x approaches 0, then this limit is 0. So this answers the second part of this exercise also, that is what the actual values of the limits are. So these are the values. Let's see the next one. It's not exactly just like this, it is slightly different. Suppose that g of x is less than or equal to f of x, which is less than or equal to h of x for all x not equal to 2. That means for all real numbers x except 2. At 2, what happens to these inequalities we don't know, and it's not given, okay, it's not a part of our hypothesis. And suppose that something else is also given. Limit, of course, limits of these outer functions are given. And both of them equal minus 5. Okay. Can we conclude anything about the values of f, g and OK? Can we conclude anything about the values of f, g and h at x equal to 2? Is it possible? Could f of 2 be equal to 0? That is another one. Could limit of f of x as x approaches to be equal to 0? Give reasons for your answers. Okay. So we can immediately see from the hypothesis that we are able to directly use the sandwich theorem in this case and conclude that this limit must be equal to minus 5. Okay. So let's do that first. So that will immediately answer this question, this part, that it cannot be 0. By the sandwich theorem, this limit is equal to minus 5, and let's also mention that this is not equal to 0. Which is not equal to 0. Okay, now we know that say let's concentrate on the limit of g only. Okay, g is a function whose limit at x equal to 2 is minus 5. Now we have seen this many times before, that this limit being minus 5 has actually nothing to do with the value of g at 2, which may or may not even be defined. G of 2 can be anything. It can be minus 5, or it can be something else, or it in fact may be nothing. That means it's not defined. G is not defined at 2. And the same is the case with H and also F. So we cannot say anything about the values of F, G and H at x equal to 2 from the present situation, from the knowledge of these limits. Anything about the values of F, G or H at x equal to 2, and in fact these functions may not be defined at that point at x equal to 2. And because of this independence of the functional values at 2 and the limits being minus 5, we can in fact have f of 2 equal to 0, or in fact anything else also, without disturbing these other facts, that limit of all the functions equal minus 5 as x approaches to. Without disturbing this fact, we can change the values of f, g and h at will at x equal to 2. Okay, so that is the solution. Next, yeah, if limit as x approaches 4 of this function f of x minus 5 over x minus 2 is equal to 1. If this is given, find limit of f of x. Okay, it's absolutely straightforward, but still let's see the solution. It's just a simple application of the limit laws, that is theorem 1. Y theorem 1. Let's start by writing 1 first, okay, and then we apply we use theorem 1 to this limit. So it's given that 1 is equal to this, okay. Now it is tempting, okay, let me just show you something that I have just now realized after writing this. It is tempting to use theorem 1 at this stage and write the next step like this. Okay, and then you solve for this limit and you get the value. But there is a slight problem in doing so. That's because we can apply theorem 1 only when we know that the functions we are dealing with all have limits. Well, the functions that you see here, I mean, if we break this thing down into its components, we see 4 things here, right? One of the functions is our f, the other one is constant function 5, there is this third function x, the identity function, and then we have the constant function 2. Now we know that these 3 functions have limits, okay, as x approaches 4. But do we know that this limit even exists? Nothing is saying that it exists, right? So how can we apply theorem 1 here? We cannot apply theorem 1 just like this. Instead, we have to do a little trick here. So that means we cannot start the solution like this. It's a very subtle thing. It's very easy to just simply go like that and finish the solution, but that will be slightly problematic. It will actually not be rigorous, okay? You may be thinking that you are applying theorem 1, but that application would be wrong. Instead, let's do this. Consider the function I think this is how I can do it. Consider the function. I'm going to consider or define another function -1 where x is not equal to 2. This of course I can do. I mean, f is after all some function, no, some well-defined function. So I can consider this function, this quotient of f of x minus 5 and x minus 2, from which I can remove 1, which is a constant function. So I can consider this function, but to make it well-defined, I have to add this extra condition that this is my new function g for all real numbers x except say 2. Now if the original function f is not defined at 4, because we are just simply talking about limit, right? Nothing is said about that here. So we have to include that also. So let's just include that also, because in this limit, I mean, this limit being equal to 1 has nothing to do with the value f of 4, which may not even exist. We don't know. So let's include, or rather exclude 4 from the domain of g. Okay, so here we are looking at a new function g whose domain is the set of all real numbers from which 2 and 4 have been excluded. Alright, now what is given? You see, it is given that this function, only this much, okay, that you see here, has limit, and that limit is 1 as x approaches 4. And what is the limit of the constant function 1 as x approaches 4? That limit also exists, and it's that constant 1 itself. And here you don't have any problem in applying theorem 1, because theorem 1 says, I mean, among all the parts that we have in that theorem, the part that says about the difference of two functions, it says what? Say you have two functions there, alpha and beta. Suppose the limit of the first function is L and the limit of the second function is M, where x is approaching the same real number C. Then the limit of their difference is the difference of the limits. That is one part of our theorem 1, and that we can use here now. There is no problem in using that now. So the limit of g of x would be the limit of this minus the limit of 1. Limit of this, as x approaches 4, of course, the limit of this is 1 minus limit of 1 is 1, so that means it will be 0. Now, by theorem 1, limit of g of x is equal to 0. Okay. Now note that now this is something we have come to know about g of x just from its definition and that limit. But now what we are going to do, we are going to use this equation and express f of x in terms of the remaining things. So note that, can I write it directly? Let me do it there. What will f of x be? One will go on this side, so we will have g of x plus 1. Then if you multiply by this and take 5 on that side, so you will get this. F of x will be x minus 2 times g of x plus 1 plus 5. Now you look at this. Now you know that this is a combination of several functions. I mean, f, the way it has been expressed, it's a combination of several functions. First we have this function g of x plus 1, and then we have that polynomial function x minus 2. We have taken their product, and with that product we have added 5. That is f of x. Now we know that limit of g of x exists, and that is 0. So limit of g of x plus 1 also exists, that is 0 plus 1 by one of the parts of theorem 1, that is sum rule. You can use the product rule also here, and then again you can use sum rule. So by theorem 1, limit of f of x exists actually. Okay, so that is one part of theorem 1, and then we can find its value also. So the problem that we were encountering previously, while we were just simply directly trying to calculate the limit, is that whether limit of f of x exists or not, that we cannot discern. But now we can, we are sure that it exists, and that comes from theorem 1 and these considerations. So by theorem 1, I mean, if you use the several parts of theorem 1 at once, then you get this. And when I am writing this now, I do not mean limit of x minus 2. What I have written here is what you can see here. Limit of x minus 2. Minus 2 is separate. Times, because we know that limit of minus 2 will be minus 2. that's why. Here also similarly 1 has been written separately, plus limit of 5 will be 5. So now we just have to put the values. So this will be what? 4 minus 2 is 2, 2 times 1 is 2, plus 5, 7. So you see that because of this subtle thing of being or not being able to apply theorem 1 is actually a thing, okay? If we are not careful, then just like how I was going to solve this problem, had I done that thing, it would have actually been a wrong solution. In spite of getting the correct answer in the end, I would have made that great mistake, okay? So this is now a correct solution. Now there is, of course, exercise 50 is similar. So I am leaving that to you. Let us see 51. It has two parts which are also similar. Anyway, let me just first write it down and then we will see. If limit of f of x minus 5 over x minus 2 as x approaches to is equal to 3, find limit of f of x, and part B is also one such. If limit of f of x, the function is same, f of x minus 5 over x minus 2, and also the independent variable is approaching 2, but now the value of the limit is 4. Say if that is the case, then find the limit of f of x. So it's enough to solve any one of this. Let's solve the first one, part A. And now you know that the procedure is similar. Consider the function. So just like that case, here also you cannot just simply apply theorem 1 and write limit of f of x minus 5. In this case, you see, the authors are very clever. In that problem, deliberately they took x and made it go near 4, so that you will be tricked into using theorem 1 carelessly. Why? Let me just go back to that one, 49th one, just for a moment. So what the authors did, you just see how cunningly they did this thing. You were given this, right? So what normally we would do if we are not careful, like how I was not careful there, normally we would just simply take limit of f of x minus 5 over limit of x minus 2, and there is no problem here, except actually there is a problem, but at first glance there is no problem in applying theorem 1, that part of theorem 1 which deals with quotient. Okay, that's because once you consider the limit of the denominator, it does not become 0. So that may convince us that yes, we are on right track and let's just do it and find the value. But we still have that problem of, but then we realize that, okay, so I am considering limit of f of x separately. Does it even exist? So that raises suspicion, and then we write that separate solution. Here, however, if someone does this, gets the answer 7, they become content with the solution that, okay, my solution is right. But then they come to this part, and here you cannot even apply that thing, that quotient rule of limit, quotient law. Because if you just blindly take the limit of x minus 2 as x approaches to, that is 0. So it's not applicable. So that would tell them that something is wrong. Then maybe they would go back to this and realize that, okay, this solution is not the way they went for it, that is not correct. But now anyway we know. Okay, so consider the function again g of x minus what? The value here is 3, where you need to mention this at first. X is any real number except 2. Then by theorem 1, the limit of g of x in this case is also 0. Oh, I should have written by theorem 1, but you know. Now express f in terms of everything else, including g. So in this case it will be x minus 2 times g of x plus 3 plus 5. So by theorem 1, this times plus 5. So you can see here that well, you are getting 0 here, fine, plus 3, but this term would be 0. So here your answer is 5. And similarly the other part we can also be handled. And besides these things, you also have exercise 52, 53 and 54, which are similar in spirit. Some of these ask us to draw graphs, which of course you have to take the help of that online facility, or if you have an electronic graphing facility with you, you can take the help of that in drawing the graphs of the functions that are given there and then doing some tests with them. Okay, so you go through these things and please let me know if you don't get something, if you have some doubt, or if you are unable to write the solutions to these exercises. Please let me know in the comment section below. So this just ends this section. In the next calculus update, we are going to see the next section, where we are going to see target values and formal definitions of limit. So far what we have been doing in that we are using the intuitive approach to limit, right? We are just considering the limit to be that value towards which the functional values approach as the independent variable approaches some value. But in the next section we are going to make it rigorous and see the actual definition of a limit in terms of target value, something called target values. So we will see that in the next calculus update when that comes. And let me just end the video here itself. And tomorrow also we have our usual update, and tomorrow let's solve algebra problems from Lee. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.